Hey kids, Creepy Baby here with our first physics podcast. As you can see, our first topic here is analyzing graphs of motion. We can use these graphs to look at how a particular motion measurement changes over time. On the flip side of this card, we've got our graphic organizer that tells us what to expect from different types of motion graphs. I want to start by giving a few definitions of some of the terms that appear here. Displacement is simply how far an object's moved and which direction from its original starting point. Velocity, how fast an object's going and which direction it's traveling. And acceleration is the rate at which velocity is changing. Now, with velocity and acceleration, there's average and then there's instantaneous. Average is simply the overall change over overall time. Instantaneous is what's happening at any one particular second. Some of those differences will become a little more important when we look at equations. As we look at the relationships here, we can see that the slope of a displacement versus time graph is the velocity. And the slope of a velocity versus time graph is the acceleration. Now, if you happen to have an acceleration versus time graph, the area underneath that graph gives you the change in velocity, and the area underneath a velocity graph will give you the change in position or the displacement. We've got a couple of examples to look at here to look at these slope and area relationships. If we start with a simple distance versus time graph, you can sketch any kind of pattern on here, and we'll just make a couple of scribbles. Now, for the purposes of this, consider all these lines to be straight. If we look at the slope of each of these segments here, we can see that something different happens to the motion over time here. We look at the positive slope, and we would say that this would be a positive velocity. Now, since we have no slope right here, we can say that the velocity equals 0. And then we can also say that during this section we've got negative slope, so this would be a negative velocity. Now, what that translates to is whichever direction we declared positive. If we just say going north is positive, we would be going north, then we'd stop and we'd come back to the south. It's always important to make sure we take this positive and negative business and try to make sure to visualize it in terms of real life directions. Notice that because these segments are straight, we're also dealing with constant velocity or constant speed over each section. If it curves, things begin to get a little bit different. If we have something that looks like this, we've got to look at the slope at different points in time here. And since we're looking at specific points in time, that would be instantaneous velocity. I can use my pencil to kind of approximate the slope here. And we can see that over this portion, the slope is increasing. That would tell us that we've got an increasing velocity or a positive acceleration if we're letting everything be in the positive direction of the initial motion. But then we start to see our slope decline. Again, in a standard frame of reference, this would be a negative acceleration because our slope is decreasing. So what we can do is we can make decisions, or we can make assertions about velocity and acceleration by analyzing what's happening to the slope, or what is the slope at any point in time. Once again, our slope is increasing, meaning an increasing velocity. And then up here, our slope is decreasing, meaning a decreasing velocity. You can also have velocity versus time graphs. We just change this here, velocity, and then our units will become meters per second versus time. And let's deal with straight lines to make our example a little bit easier here. If we have a velocity versus time graph, make two different sections here. Now it's important to make sure that we don't use distance rules to analyze a velocity graph. If we were using distance rules, this third section, we might say we were traveling in the opposite direction. But you can't say that with this graph, because notice that being above the x-axis here, we've got a positive velocity the entire time. We're always moving forward. Now, if you look at the slope of this, we'll have three different accelerations. We've got a positive acceleration, we've got another positive acceleration but lower in magnitude, and then we've got a negative acceleration. Our object would still be moving forward in this section, but it would be getting slower while still moving in that initial positive direction. The only time that our object's at rest is in the very beginning, because the velocity touches zero here. So this would be positive acceleration. This would be a smaller positive acceleration. And then this would be a negative acceleration. We've got an example of an AP problem here. And before we do that, there's one more thing to look at here. If we look at the area underneath a velocity graph, what you have is the displacement. Now, if I just let my units here be 1 second and 1 meter per second, we could estimate here we've got about 2.5 here, we've got about 2 here. So our delta x would equal the area, which would be 1/2 times 2.5 times 2, which would come out to 2.5 meters of displacement. Now, if you started at the 0 meter line, you're now at a location of 2.5 meters. But if you started at the 50 meter line, you'd be at 52.5 meters. And so here we've used the slope to decide what's happening to the acceleration. We use the area underneath the graph to decide what's happening to the displacement.